let us continue with the derivations that we have been doing. We started out with the 3-phase machine, 3-phase induction machine, where the rotor is an ABC reference frame and the stator is also in the ABC reference frame. That was the natural reference frame description of the induction machine. From this we have gone to the 2-phase induction machine, where the rotor is in alpha beta reference frame and the stator is also in alpha beta reference frame. We will mark this is the rotor and this is the stator. Alpha beta reference frame is the reference frame attached to the rotor 2 axis and therefore it is rotating. Alpha beta of the stator is fixed to the stator and therefore it is stationary, and to do this we have used the power invariant transformation, which means that if the number of turns here was n ABC per phase and then this then goes to n alpha beta, where n alpha beta is root 3 times n ABC by root 2. So you have number of turns here that are different from the number of turns in the 3-phase machine while converting it to the 2-phase equivalent using this approach. And then from this we have gone on to the stator reference frame, all referred to the stator. That means the rotor is now referred to pseudo stationary coils in the alpha beta of the stator, and the stator remains as it is in the alpha beta reference frame. In doing this, again we have used the condition of power invariancy, but in this case the number of turns still remains the same as what was here. Therefore the number of turns in the windings now is different from that of n ABC. We have gone from n ABC to n alpha beta given by this relation, and between these two the turns, number of turns remains the same. And therefore what we have, the resultant system is you have the beta S axis and then you have the alpha S axis and you have the coil on the alpha S coil, this is the stator coil, and then you have the stator coil on the beta S axis, and then you have the rotor coil which is now referred to the stator, and here again you have the rotor coil referred to the stator. So this is the rotor referred to stator, this is also rotor referred to stator, whereas this is stator and this is also stator coil. Note that we have in these, between these two coils, the dot points are here and the dot points are here, which means the current is flowing into the dot point here, current is flowing into the dot point here. Similarly you have currents that are flowing into the dot point. So this is now the description of the machine. All coils are stationary with respect to each other, and for this we have derived the electrical system equations. So let us put that down also here. You have V alpha, V beta of the stator, and then V r alpha and VR beta for the rotor. So, this is the left hand side vector. This is then equal to, yesterday we wrote down the operational impedance form in the last lecture. So, let us put that down. You have Rs plus Ls bar into P, and then 0 here, you have MSR bar into P, and then 0 again, you have 0 Rs plus Ls bar into P, 0 MSR bar into P, and then here you have MSR bar into P and MSR bar into omega R, RR plus LR bar into P, and then LR bar omega R minus MSR bar into P, and this is omega R and MSR bar P minus LR bar omega R, RR plus LR bar into P, multiplied by the vector of currents. So, I alpha, I beta, I R alpha, and then I R beta. So, this was the description that we had derived in the last lecture. Now, let us look at this description a little more closely. We know that Ls bar is nothing but the leakage inductance plus 3 by 2 times LMS as we come down from the 3 phase description to this, and MSR bar is nothing but 3 by 2 times MSR. Similarly, you have LR bar is nothing but LLR plus 3 by 2 times LMR. So, these are the equivalents. If you come down from the 3 phase, this is what you get. So, let us look at this expression a little more closely. If we look at the first equation, that for V alpha, we are basically writing down the voltage equation for the excitation given here. This is applied a voltage V alpha here, and we find that V alpha is given by Rs into I alpha plus Ls P I alpha. This is nothing but the resistance drop plus the self inductance drop, and then you do not have any term here, which means that there is no drop caused here due to flow of current in beta S coil, which is to be expected because this coil is there at an axis which is 90 degrees away from this. Therefore, the mutual inductance term would be 0, mutual inductance is 0, and that is indeed what we see here. Here you have MSR bar into d IR alpha by dt, which means that there is a mutual inductance between these two, and that is again to be expected because these two coils are on the same axis, and therefore any flow of current here, any rate of change of current here would induce an EMF here defined by the mutual inductance. So, that term is what we see here, and this term is 0. This refers to the flow of current in the IR beta, and this says that there is no effect of current that is flowing here on this coil, which again intuitively one may say this coil is at an axis 90 degrees similar to that of the beta S coil, and therefore there is no induced EMF here, and therefore this equation can be written down directly by observation, looking at the fact that you have these two coils situated on one axis, these two on the other axis. Similarly, when we now move down to the second equation, the second equation also we see is similarly arranged to the first. You have Rs plus Lsp for the self term, flow of current I beta, and you have a mutual inductance term that occurs due to this. So, a self term due to this and mutual due to this. There is no mutual term between these coils because they are at an angle of 90 degrees. Let us move down to the third equation. In this equation we are writing down an expression for the voltage in the coil here, the rotor coil referred to stator as seen from the stator, and here we find that you have MSR P into I alpha, which we can expect because these two coils are on the same axis, and therefore if there is a current flowing here it would have an induced EMF here defined by the mutual inductance, and therefore this term is alright, MSR into P times I alpha, that is d by dt of I alpha. But now you find that there is another term which is an induced EMF but occurring due to speed. This term is MSR omega r multiplied by I beta, and this term occurs due to flow of current in a coil which is at 90 degrees to it, and therefore it is multiplied by I beta, and this EMF term depends upon speed, and therefore this kind of term is given a specific name. It is called as a speed EMF term. So speed EMF term is so called because it appears to arise due to speed, for if the speed were equal to 0 then this term would vanish, and this term does not depend upon di by dt, it is simply MSR omega r multiplied by I beta, whereas these terms MSR P similarly here and here, they arise not due to speed, there is no speed term in any of these things, they arise due to di by dt. If di by dt were 0 then such of those terms would be 0, and therefore those terms are called as transformer EMF terms. Transformer EMF term. So these are multiplied by omega r or some speed, these are multiplied by di by dt, and then you have the self term which is the resistance drop plus the self inductance drop, and then again you have a speed EMF term, and we notice that this speed EMF term arises due to IR beta, and therefore you see that this speed EMF term as well as this speed EMF term arises due to coils that are in beta axis occurring in a coil on the alpha axis. So the voltage equation of a pseudo stationary coil on the alpha axis now has speed EMF terms due to flow of I in an axis 90 degrees away. Therefore this has speed EMF terms due to this current and this current. When we come down to the next equation, that is VR beta, you see that there is a speed EMF term here, this again is due to a current flowing in the alpha axis. So if you now look at the equation for this coil, this has speed EMF terms due to flow of current here, and it should also have a speed EMF term therefore due to flow of current here, which indeed is true, there is a speed EMF term here and there is a speed EMF term here. On the other hand, due to another situated on the same axis, you have a mutual inductance term which is MSR into P, and finally you have the self term which is the resistance drop plus the self inductance di by dt. So what we find from this is that transformation to the stationary reference frame brings about new terms in the impedance description which arise due to speed that is there. So you now have speed EMF terms and transformer EMF terms. we find further that the speed EMF terms arise from quadrature excitations or quadrature currents or quadrature coils. And we also note another thing, speed EMF terms arise from these and are present in pseudostationary coils. For example, speed EMF terms do not occur here. In these two expressions which are not for pseudostationary coils, V alpha and V beta are really stationary because they pertain to the stator coils, there are no speed EMF terms, whereas in these two coils there are speed EMF terms, and these coils are pseudostationary coils having come from the rotor. So, you find speed EMF terms in the pseudostationary coils, and those speed EMF terms arise due to coils on the other axis. Alpha speed EMF term arises due to coils on the beta axis, beta speed EMF term arises due to coils on the alpha axis. And we also find that the speed EMF term is negative for all terms on this axis, not negative for terms on this axis. So, these are some of the observations that you make. This is how this appears to have been formed, and having understood this, one can extend this for more situations. Suppose you now have a hypothetical machine, let us say it has one more coil here and one more coil here as well, and let us say that these are again pseudostationary coils, this coil and this coil. So, if we are to consider a machine like this, then maybe what we could call this as we could call this by, let us say, VR1 alpha is the voltage that is applied here, and let us call this as VR1 beta for the voltage that is applied here. So, that means you would now have two more equations here, VR1 alpha and VR1 beta. You will have two more flow of currents, IR1 alpha and IR1 beta. So, how would you then augment this operational impedance description to include these two also? That is fairly simple. Having understood the way the operational impedance description looks like, one can now augment this. If you are to write an expression for VR1 alpha, this is a pseudostationary entity, and therefore you will have, with respect to I alpha term, you will have a mutual inductance term. Let us call that as MSR1. It may not be the same mutual inductance between these two. So, MSR1 P I alpha, and then you need to have a term with I beta. This is pseudostationary and you have beta on the other axis, and therefore there will be a mutual inductance term and a speed EMF arising due to that, omega r into I beta MSR1, and then you are looking at the flow of current here, that is the third term due to this. So, you have the third term arising, it is again between this coil and this coil. Therefore, if we call that as MSR2, then MSR2 into P. This is a di by dt term because you are referring to an IR alpha which is on the same axis, and then you will have an MSR2 omega r into IR beta IR beta is a current flowing on the other axis, and this being a pseudo stationary coil, there would be a speed EMF due to this, and then you have its own. So, R, let me call it RR1 plus LR1 into P times IR1 alpha, this is the self term, and then it would also have a speed EMF term due to the flow of current here, and that is LR1 multiplied by omega r into IR1 beta. So, having understood how this operational impedance matrix looks like, one can therefore write down the expression for any number of coils on the alpha axis and the beta axis. It allows us to write this down by observation. Now, this description of an electrical machine which we have drawn here, there is one coil here, another coil here, maybe more coils, similarly more coils. This is a description, this is the name given to this kind of a description is that of a electrical, why it is now given a name like that? We have derived this machine description starting from an induction machine. We started from a 3-phase induction machine and then a 2-phase, and then we referred everything to stator. But as we go along, we will see that this machine description what we have derived can be used to describe any electrical machine that falls in the group of machines that we are looking at. For example, this machine can also be used to describe a DC machine. It can also be used to describe a synchronous machine. It can also be used to describe an induction machine. And we know that if you look at a DC machine, DC machines are again of various varieties. You have separately excited machines, you have shunt excited machines, you have series excited machines, and in this case again you have long shunt, short shunt, and then you have compound machines. In this case you have cumulatively compounded, you have differentially compounded machines. So, DC machines itself are of various varieties. One can go on to see, we will look at that in a little while, that all these machine descriptions can be arrived at from a machine description like this, where there are some n coils on the alpha axis and n coils on the beta axis. The DC machine can be seen that few of the coils here could be removed, few coils here could be removed, and you get a particular kind of DC machine. Depending on the way you interconnect them, you get other kinds of DC machine, and that is why this is given this name. Because this can also describe a synchronous machine or an induction machine, one can then say that this forms a generalized machine description. It is also a generalized machine description from which one can, by specific constraints imposed on the variables, one can arrive at various forms of electrical machines. Now, we have been all along looking at the electrical equation. Let us also see what happens to the generated torque. Now, this description, the generalized machine description, we have written it in the form V equals some Z into I, but this can also be expanded. So we can write this in the form VR alpha beta equals R into IR alpha beta plus L alpha beta into PIR alpha beta plus G IR multiplied by omega r. So we had indeed written the equation, the derivation that we made in the last lecture brought about an equation in this form, and then we compressed it into the operational impedance matrix. It helps us again, it helps to expand this in a similar form here. So this is the matrix that we have. Now in order to derive an expression for the generated electromagnetic torque, let us look at the 3-phase machine we started out with, or rather the machine here, the 2-phase machine. We started out with an expression which looks like this: V alpha beta equals R into I alpha beta plus P of L alpha beta into I. This was the machine description with which we started out, and starting from our basic definitions, the way we derived the electromagnetic generated torque, you would remember that the way we started this out was, in order to derive this expression, you then consider the input power. Input power is given by I alpha beta I transpose into V I transpose V is nothing but I transpose Ri plus I transpose P of L I. This approach is what we discussed right at the beginning, the first several lectures. In the first several lectures, an approach to derive forces, approach to derive the electromagnetic generated torque we discussed, and that is what we are now trying to recollect. So input power is like this, and we know that in the machine input power must be consumed in primarily 3 different ways. One is the resistive losses, another is the mechanical output, and then the third is the rate of change of field energy. I am just putting this down so that one can recollect what we had heard several lectures earlier, and from this, in order to get the mechanical output, mechanical power output, in order to get this thing, we started out with an expression for the magnetic stored energy. I think we called it as WF, that is given by half of I transpose L into I, in whichever reference frame we are considering it, and then the rate of change of field energy is nothing but the derivative of this. So dWF by dt is equal to d by dt of half I transpose L into I. Now we can simplify this expression and apply it to this derivation to this equation in the alpha beta reference frame. And if you remember, the expression that we landed with was the generated electromagnetic torque is half of I transpose dl by d theta multiplied by I. So this was the expression that you would get if you proceed. All that we had to do is differentiate this, that gives the rate of change of field energy. The expression for input power is there. We know that this term is the resistive loss component, and then after having differentiated this, if you subtract that from this expression, the remaining term would then basically give you the mechanical output that you have. But our goal now is not to derive the expression in the alpha beta reference frame. We want to derive the expression for the generated torque in the stator reference frame, that is pertaining to this equation. So in order to get that, we now need to basically replace these terms I with the flow of currents in the stator reference frame, and for that these currents are now I alpha beta alpha beta. For this we use the relationship I r alpha beta is equal to the transformation matrix, we called it C I think. So alpha beta, this was the relationship that we wrote, and therefore we have I alpha beta equals C inverse I r alpha beta in both are now in the stator. So we replace these expression, these vectors I with this expression, and let us see what we get. So you have dWf by dt equals d by dt of half of C inverse I alpha beta, C inverse is what we have to put, and we know that C inverse is nothing but C transpose. So you have C transpose I r alpha beta, and maybe I will put a flower bracket here since there are now more brackets. So transpose of this matrix multiplied by L alpha beta multiplied by C transpose I alpha beta r. So this is your expression for dWf by dt in the stator reference frame. So let us expand this. So this is nothing but d by dt of half of I r alpha beta transpose multiplied by C L alpha beta C transpose I r alpha beta. Now in this expression we have seen in the last lecture that this term C L C transpose is the same as L alpha beta, and therefore we can write this as d by dt. Instead of d by dt I will simply say P half I r alpha beta transpose L alpha beta multiplied by IR alpha beta. And now we need to differentiate this, and since there is one term, second term and a third term, we have to differentiate them one by one. So this differentiation gives us half of PIR alpha beta. So this is one term multiplied by L alpha beta into IR alpha beta. This is the first term, and then you have the second term, which is half of IR alpha beta multiplied by P of L alpha beta multiplied by IR alpha beta, and then the third term gives us half of IR alpha beta L multiplied by P times IR alpha beta. So these are the three terms that come about on differentiation. In these three terms, if you look at the first term and the last term, this matrix L alpha beta is a symmetric matrix, and therefore if you are going to multiply this matrix with PIR alpha beta here and PIR alpha beta later, these two being the same, this term and this term therefore would be identical, and that therefore gives us IR I have missed a transpose here, so there is a transpose here and a transpose here. So this is IR transpose alpha beta into L alpha beta into P times I alpha beta. This is the sum of the first term and the last term. If you look at the second term, this is the derivative of L alpha beta, and from our derivation yesterday and indeed what you see today, this L alpha beta does not have any term that depends on T. This is all terms are basically constants, and therefore derivative of this matrix is 0, and therefore this term goes to 0. Therefore dWf by dt is only this part. So if you now apply the same logic whatever we have done here, that is obtain an expression for the input electrical that is given, electrical input power, then you have to multiply this by I transpose. You have I transpose here and I transpose here, and then you know that the resistive loss component is due to this, and the remaining term must now be the mechanical output plus the rate of change of energy, and this rate of change of field energy is what we have derived now, and that is I transpose L into Pi, and that indeed would be your second term if you multiply by I transpose, and therefore I transpose G into I into omega r gives you the mechanical output, and therefore one can say that the torque that is generated in this expression is nothing but I transpose, one can call it IR transpose alpha beta into G multiplied by I. So this is the expression for the generated electromagnetic torque. Now one can expand this and try to simplify this expression in terms of the actual flow of I alpha, I beta and so on. So this expression for torque can be written as follows: I alpha beta transpose is nothing but I alpha I beta I r alpha I r beta. The matrix G is nothing but 0 0 0 and 0 MSR bar 0 LR bar minus MSR bar 0 minus LR bar and 0. This is your G matrix, and then you have again this vector I alpha I beta I r alpha I r beta. So upon simplifying this, what you have is I alpha I beta I r alpha I r beta multiplied by the first row multiplied is obviously going to give you 0, second row would obviously give again 0, then you have MSR bar multiplied by I beta plus LR bar multiplied by I r beta, yes, and then the last row gives us minus MSR bar multiplied by I alpha minus LR bar multiplied by I r alpha. So if you multiply this out, the first two terms are going to multiply with 0, so there is no problem. In the next two terms you see that I r alpha multiplying here LR into I r beta. Similarly you have here these two terms. So this term and this term will contribute to equal and opposite terms, and they simply nullify each other, and therefore the resultant is nothing but MSR bar multiplied by I beta into I r alpha minus I alpha into I r beta. So this is then the expression for the generated electromagnetic torque in the machine. So this equation and this equation together now describes the full electrical machine, electrical system and the mechanical system. One can use this to solve for the dynamics of the machine in whatever manner we want. So this then completes the machine description in the stator attached reference frame. We have seen how the machine description can be extended for a machine with more terms in the alpha axis and in the beta axis. We started out with the induction machine, so let us now complete one more aspect. We have seen how the machine description is going to change when you switch the reference frames. Let us also see what happens to the supply variables. In the induction machine, if we look at the induction machine as the example, we started out with the three phase was converted to two phase, and therefore let us look at the two phase machine. This has two windings on stator and two windings on rotor. Now because it is an induction machine, the way you would normally operate an induction machine is to give excitation on the stator and the rotor will be shorted. You do not give supply to the rotor windings. The rotor of an induction machine is normally shorted, and the stator is given the electrical supply. So you would apply a source voltage is applied on this. It is an AC voltage, and we will therefore say that AC voltage of supply frequency is, let us call it as omega s, that is the supply frequency. Since this is going to be a short, there is no applied voltage there. Now in an induction machine, you know that the rotor rotates at a speed omega r, which is less than the synchronous speed of the rotor, and the rotor is therefore going to have currents in the rotor are therefore at the frequency of the slip, which is r at slip frequency, which is nothing but omega s minus omega r. So flow of currents in the rotor is likely to be at a much lower frequency. Normally the slip is small, and therefore this frequency is quite small. This is the current that is going to flow in the rotor. In attempting to go to the stator reference frame, what we have done is we have transformed these currents that are flowing in the rotor. We tried to determine an equivalent current that will flow in the stator that will produce the same MMF, and in order to do that, what we have done is that use this expression IR alpha and IR beta is equal to cos theta minus sin theta and cos theta multiplied by your I alpha and I beta. Now this I alpha and I beta are the currents that flowing in the rotor, and therefore I could simply say that this current is some Im cos of omega s minus omega r into t plus probably some phase angle as well, and therefore this current would be Im sin of omega s minus omega r into t plus the same angle phi. This would be the current. Therefore, if you evaluate the expression for IR alpha, that is then Im multiplied by cos theta cos of omega s minus omega r into t plus phi minus sin theta sin of omega s minus omega r into t plus phi, and this can therefore be written as Im into, this is of the form cos A cos B minus sin A sin B, therefore this is nothing but cos of theta plus omega s minus omega r into t plus phi. This angle, if you remember, is the angle between, we had drawn the rotor axis here, the rotor coil was actually fixed to the rotor, and this angle is the angle made by the rotor, and this is what is now going to rotate along with the rotor, and therefore this angle is nothing but, theta is nothing but omega r into t, and therefore if you substitute theta equal to omega r into t, this expression reduces to Im cos of omega s into t plus phi. This is interesting because what it says is that slip frequency currents that are flowing in the rotor, when you now look at it, look at the flow of current in the pseudo stationary stator referred axis, that now looks like the supply frequency current, right. So this is intuitive to understand, because what we are now doing in the induction machine is that you are attempting to look at the MMF that is equivalently generated by currents that are flowing here, and you know that the field that is generated by the rotor in the induction machine, if the rotor is fixed, the field moves at the frequency of the slip, but the rotor itself is now rotating at omega r, therefore the net speed at which the field is rotating as seen from the stator will be at the frequency of the supply itself, will be at the frequency of the stator field, and that indeed is the reason why now you have the equivalent flow of current now is having supply frequency. Similarly, one can derive an expression for IR beta as well. You would find that it is Im sin omega t omega st plus phi. So essentially now we have derived a representation of the induction of the machine in the stator reference frame. That means all the dynamics of the machine are seen from the stator, and in the next lectures we will see how this can be adapted in order to form various electrical machines and to describe their behavior as well. We will stop with this for today.